Okay guys, so welcome back. So in this video we are going to talk about a very important theory, which is the 18 electron rule. We can use the 18 electron rule to determine whether a complex is stable or not, right? So I will explain this by a simple example. Which we have here is manganese complex, manganese and carbon monoxide complex. So when you are finding the total number of electrons this complex has, the first rule, right, the first thing you need to do is you need to find the electrons on this metal center, which is here is manganese. Just ignore all the charges, do not think about the oxidation states, just take the manganese and find the electrons in the last energy level. So which the manganese contains S2d5, which makes the total number of electrons as 7 electrons, right? That's the first step, right? That's the first step. In the second step, what you need to do is you need to calculate the number of electrons which all the ligands have contributed to our metal center, right? So this is little bit a tricky part, which means like you mostly cannot logically think or logically look at the ligand and determine how many electrons will it give. Like it is little bit harder. So I have given a table in the later part of this video. Please check it out. In this case we have carbon monoxide, and just think carbon monoxide will give 2 electrons for the metal center. So now you need to determine how many electrons, the total, right, how many total electrons is contributed to the metal center by ligands. So here we have 5 carbon monoxides, which gives 10 total electrons, right? So then here we have the last step. Here we have the last step, which is if your complex contain charges, right? Let's say your complex contain a positive charge, right? Positive 2 plus 2, your complex contain a charge of plus 2. Then you need to subtract 2 from the total number of electrons. If your complex contain minus, let's say minus 2, then you need to add 2 to your total number of electrons. So in this case our complex doesn't contain any charge, so you do not need to consider about these things. So just add the total number of electrons, 7 plus 10, which is equal to 17. So this complex over here doesn't accept the 18 electron rule, right? So this is the case, right? 18 electron rule is the rule where we can say mostly if a complex contain 18 electron total, which in his valence form, it is stable. So if it doesn't contain 18 electrons, mostly it is unstable. But there are exceptions, right? There are exceptions where lower electrons or higher electrons than the 18, which makes the complex stable. So let's take another example, right? Okay, think about this one. Here we have vanadium, chlorine, CH3, PR3 and another PR3. So just pause the video and try it yourself. I will give like the chlorine is giving a 1 electron, CH3 is giving a 1 electron, and these two are giving 2 electrons each, right? I will give you the table at the end of the video, right? You can just go to the table and check this out. So pause the video and try it yourself. Let's say palladium has total of 10 electrons, right? In its last energy level, palladium has 10 electrons. You can check it easily by a periodic table. Then you find the total electrons which is contributed by the ligands in our second step. Here we have chlorine will give 1 electron, CH3 will give 1 electron, PR3 will give 2 electrons, and here we have 2 ligands of pr3. So the total electrons will be 10, 11, 12 and 14, 10, 12 and 16 electrons. So which we can say this is also not accepting our 18 electron rules. As you can see, there are no charges, right? There are no charges, so we do not need to consider about it. So the next example, let's take a example with a charged one. Here we have platinum, and here we have chlorine, here we have chlorine and another chlorine and olefin. The total charge is minus. Okay, now try it yourself. Pause the video and try it yourself. So if I do this, we have platinum. Find the total number of electrons in its last energy level. Just do not consider anything about its oxidation step, right? You do not need to consider anything about it. Just find the electrons of the platinum. Platinum contains 10 electrons. Platinum contains 10 electrons, and then the second step, you need to find the total number of electrons which will be contributed by the ligands. Here we have chlorine. Chlorine will give 1 electrons, but there are 3 chlorine ligands, which total gives 3 electrons, right? And then we have our olefin. Olefin will give you 2 electrons. So the total number of electrons will be 15. But don't forget, there is a charge. Now here's the rule. If there is a minus, then you need to add. So here we have minus 1, which means we have to add 1. We have 16 electrons. Let's move into another one. So in this case, okay, so let's take about this one: cobalt, NO and 3 CO groups. So pause the video and try this by yourself. Here our cobalt will has S2 and D7, which will have the total electrons of 10, right? So then in the next step, you need to calculate the total number of electrons which will be given by the ligands. Here we have NO, which will give you 2 electrons, and carbon monoxide, which give you 2 electrons, but there are 3 carbon monoxides. So total number of electrons we have is 8. So there are no charge, so no subtraction or addition. Total number is 18. Here we have the 18 electron rule accepted. Ligand. So there are exceptions, right? Here let's take about this one. This is a very particular example for not accepting 18 electron rule, right? So I will give you this particular complex. This is a very good complex. Let's say carbon monoxide, chlorine, CNR, right? So you have to calculate the number of electrons in this case. So pause the video and try it out yourself. So in this case, let's say our metal center contains 5 electrons, which has S2 and D3, and then the number of electrons from the ligands, right? So here carbon monoxide will give you 2 electrons, chlorine will give you 1 electron, and CNR, which is carbon has to give 2 electrons. Here phosphorus is also giving 2 electrons, and there are 2 atoms which are contributing. So the total number of electrons here will be 14, right? So like this one, there are exceptions, so this is very fun, right? Okay, so here I have shown you the diagrams of how each ligands can contribute to our metal center by giving electrons. So here we have 1 electron donors, basically like CH3, CH2R groups, hydride groups, Br, iodide, NH2OR. Here the chlorine is also present, right? So benzene ring here, like, don't get complicated, right? Here we have the benzene is connected to our metal center through this bond, right? Not through this 5 electron cloud, just by a sigma bond. That's why we are taking it as a 1 electron donor. So there are 2 electron donors, which here we can say carbon monoxide, like these things. These are basically 2 electron donors. If you see these ligands connected to your metal center, which means they have contributed 2 electrons to your metal center. So when you are calculating the 18 electron rule, so you're calculating the electrons of your complex, you need to take 2 electrons for these kind of ligands. And then here we have 3 electron donors. I need to tell you about this notation. Here we call it a neat notation. So I will take an example like this, right? So this thing over here, so let me take another color. Let's do that. Okay, here CH2 CH2. So here we have a 5 electron cloud over here. This is neta 3, which means this ligand over here is connected to our metal center through 3 carbon atoms. 3 carbon here, neta 3 means 3 carbon atoms are connected to our metal center. So here this is connected like this. All these 3 carbon atoms have connected to our metal center. So let's take another example, so which we are talking about in the next things. Let's take this one. This is a cyclopentadienyl ion, cyclopentadienyl ion, right? So this is basically neta 5, which means 5 carbons have connected to our metal center. Here we have the metal center, and here we have 5 carbons which have connected to our metal center. Basically this notation is represented the how many carbon atoms have connected to our metal center. I hope you got the point. So here we have the 3 electron donors, and another term, this bridging halides. Let me explain it quickly to you about this bridging halides. So let's assume we have a halide. Let me clear this up first. Okay, right. Okay, so let's take a halide. Let's say chlorine. Let's take chlorine, chloride ion. So you know, when a chloride is connected to our metal center, this is donating 1 electron, right? Chloride is a 1 electron donor, but there are vacant electrons all over the chlorine atom, so this can bridge to another metal center, right? This can bridge to another metal. This is called the bridging. So here one halide or one ligand which is connected to 2 metal ions, which is called the bridging phenomenon. So I hope you got the point, the neat notation and this bridging phenomenon. So here we have the 3 electron donors, and we have 4 electron donors. We have 5 electron donors. As you can see here, neta 5 means all these 5 carbons are connected to our metal center, neta 5 pentadienyl. And here we have 6 electron donor, which is a benzene ring, neta 6, which means the all 6 carbon atoms is connected to our metal center, right? So we need to use this table of these details when we are calculated, when we are using the 18 electron rule.